talking about computing the similarity of S1 and S2, two sequences. And remember the definition. We defined alignment. We've seen many alignments now. It's the max over all alignments of S1 and S2. Max of, now we're going to go back, for the purposes of beginning to understand how we compute similarity, we're going to go back to our simplest definition, even though last time we were talking about all the ways that are important in biology to make that definition more relevant. Maximum number of matches minus the number of mismatches minus the number of spaces, or indels. Okay? So this is our objective function. We want to find an alignment that maximizes this sum. And there are so many alignments that it's absolutely out of the question to have a method that would simply enumerate, look at all the different alignments, and calculate this value for each one. So we need an efficient method, a very efficient method. What does efficiency mean? Of course, it means, generally speaking, that it runs quickly or that it doesn't consume a lot of computer memory, because that might be something else that isn't available. But certainly, time is important, or speed is important. And secondarily, memory, computer memory. Now, if we're talking about speed, first of all, you have to realize that the time that a program or an algorithm takes to compute something, to compute the alignment, the best alignment, or the similarity value, is probably going to increase as the size of the sequences, the size of the strings increase. You know, huge strings just seems intuitive are going to take much longer to do those alignments than short ones. So when we talk about speed or efficiency, we're always going to talk about it as a function of string length or size. And just as we computed, when we calculated the number of alignments, we just assumed that both of the sequences were going to be of the same length. We called them n. So now, I mean, we had a variable. We didn't talk about how many alignments are there when your two strings are of length 10 or so on, although that's what you can compute by the program that's available on the web. We had a parameter for those two strings. So one is length n, and the other one is length m. And they may both be the same in some of our discussions if we want to simplify things a little bit. But anyway, we have abstractly two lengths, n and m. And we realize that as n and m increase, certainly one could expect that the speed is going to, the time is going to take longer. It's going to be longer. Time is going to be longer. That's terrible. It's going to take more time, okay, as n and m increase. All right. But how do we actually clock that? Do we want to sit there with a real watch and talk about wall time? Well, that certainly is going to be dependent on what computer you actually run on, or other aspects of the computing system. So we want to be more abstract because we don't want to say, you know, on your PC, Pentium 2, it's going to take this much time as a function of n and m, and on some other machine, it's going to be something else. So what we look at is we use number of operations needed to compute similarity as a function of n and m. Okay, so that's how we're going to clock. That's how we're going to talk about whether a particular method is fast or slow. How many actual operations does the algorithm use to compute the similarity as a function of n and m? And what do we mean by operations? Well, that'll depend on a particular algorithm. Sometimes it's additions, arithmetic operations, or comparison operations, or looking up a particular number in memory operations, things of that sort. All right, all this will become clearer in a moment in this lecture, I hope. All right, now okay, so that's what we're going to do today, is begin to talk about how we're going to compute similarity very efficiently. Now, it turns out that in all these discussions of algorithms and of alignment generally, it's very useful to use what's called an alignment graph. And alignment graph is really a very simple object, and I happen to have one here. So that didn't help. Okay, can the camera focus in on this? Hello? At any rate, guess there's nobody home there. So what we have here, this is an alignment graph for two sequences. This is what I'm going to be calling S1, Dan, and S2 is going to be the other sequence that's written there, S1, S2. So I'm interested in the alignment of S1 and S2 and computing the similarity of those two sequences. So what the alignment graph has is one column for each letter, and it also has a zero column. And for each letter in S2, it also has one row for each letter in S1, and it also has a zero row. Okay? Now, and then it has these little boxes here. It has these nodes for every row-column intersection. So we have a total of 4 columns numbered 0 through 3, and in this example, 4 rows 0 through 3. And we have a node here at every row column intersection. And then we have one of these little boxes for each 4 neighboring nodes. And the box just consists of an arrow that goes horizontally to the right, one that goes vertically down, one that goes diagonally, and then here's another horizontal and another vertical. And notice that there's a direction to each one of these arrows, and they all either go to the right, or they go down, or they go down and right. Okay? So now what I want to explain is that each path from the 0, 0 to this node over here. Each legal path, a legal path is one that is obeying the direction of the arrows. Okay, it's not legal to go opposite an arrow. You'll get a moving violation that way. And each path from here to here that obeys the arrows describes an alignment. Okay, well, that's the first thing I want to claim, because that will help us later figure out what the best alignment is. So here's a claim. Okay, each path from 0, 0 to NM. Okay, so we're starting at 0, 0, but we're ending up at the point that's NM. Little m for the lengths of the two sequences, i.e. the lower right node. Each such path defines an alignment of S1 and S2. And here's the way you do it. In that path, if you take any particular path, if the path goes along a diagonal, then we'll put the character that's on that row. You look at the node that the arrow is going into. The character for that row and that character for that column will be placed opposite each other. So that's going to be the meaning of a diagonal. Whenever you have a diagonal, you'll take the two associated characters and place them opposite each other. So remember, we're trying to create an alignment from a particular path. And I'll show you examples of this in a minute. Whenever you go along a horizontal, okay, then into this node, horizontal. Then you'll be placing the character in this column opposite a space. So in S2, you'll put the character of this column opposite a space into S1. So you'll make a space in S1 to be placed opposite that character. And whenever you go vertically, you'll be doing the symmetric thing. Vertically goes into a particular node, and the character in that row will be placed opposite a space in the other string. So I just have these three rules for how you turn a path from here to here, any path you happen to find in here, how you turn a path into an alignment. Okay? So let me write this up and show you some examples. So a diagonal edge to a point, you have a character here and a character there, means put character I of S1 opposite character J of S2. Okay? A horizontal, here you are in row I, and you're going over to J, and here you put character J of S2 opposite a space in S1. And that space, we'll see, is going to come after. Well, we'll see in a minute whether it's after or before character I. But as you're building up the alignment, it'll be right there wherever you're ready for next. And the third rule is symmetric, that a horizontal from in J, from I to I plus 1, is going to be put a character I of S2 opposite a space in S2. Okay? So let's do some examples. What happens if I take the path that goes from 0, 0 directly? Just take the one straight down here to the lower right node. What alignment is that? That's just lining up all the characters opposite each other. So that would be S1, S2. Okay? Well, that's the path that goes like that. 0, 0, and M. Well, let's be a little more inventive. What if we take the path that goes like here, and then a diagonal? So we're going here, diagonal, diagonal, and then down. What alignment does that correspond to? Well, one way of thinking about this, without looking back really at the rules, but it should be consistent with the rules, is that when I'm moving over here, really I'm using up a character of the top. The horizontal move means I'm using up a character in the top string, which is S2. As I move further and further along, I've used up more and more characters of that top string. Similarly, as I move down, I'm using up characters of the string that's here along the rows. So that's string S1. So what happens if I make a horizontal move here is I'm using up the A from Ann, but I haven't used up anything here from Dan. So what does that mean? It means you're putting the A opposite a space. There's nothing being consumed in the second string. So this first movement here puts A opposite a space. Okay? Then we're moving down from here to here. All right? Well, that rule always was put the character here opposite the character here. We're now consuming two characters. So D gets put against N. Then we have another diagonal move, which puts N against A. All right? And we're here. And now we move down. That ends up using up this N, but nothing additional is used up from S2. So this N gets placed opposite a space. So hopefully what I said in terms of using up language is consistent with these more precise rules. The using up is really the right intuition for how to go from a path to an alignment. Okay? Let's try another one, a rather silly one perhaps, where I go all the way down here and all the way over there. That's another path, right? So in that one, I'm using up the characters from S1 without using up any of the characters from S2. So they all get placed opposite spaces. That takes me down to here. And then from here, I'm going over that way. And that's using up all of those characters. And, of course, nothing new from S1. So this alignment, this path, excuse me, corresponds to that alignment. All right. Now, so the claim is that each path gives you an alignment. And I don't know whether I said that those alignments are all different, but you should be able to see that every path, two different paths give you two different alignments. Just by seeing the rules here, somewhere, wherever those paths first differ, you're going to be doing something different at that moment. And so the two alignments are certainly going to be different. Okay? If two paths are different, maybe they begin the same, but at some point, one either goes along a diagonal and the other is a horizontal or vertical, so you're going to be doing quite differently there. Or one's a horizontal, the other's a vertical. Okay, so either way, you're going to see that the alignment will be different at that point, and maybe other places as well. But two different paths give you two different alignments. Now, what's the converse statement about these paths and alignments? Converse statement is that any two alignments, well, actually, any alignment corresponds to a path. Okay? So far, all I've justified is that every path gives you an alignment. But the converse is any alignment I show you, as long as you don't have a space opposite a space, every alignment I show you should correspond to a path. And the way you would do that is you start reading the alignment left to right. And you see, in that position, are there two characters opposite each other? If so, that's a diagonal. Is it a character opposite a space? Well, what character is it? I mean, where is the character in S1 opposite a space in S2, or is it a character in S2 opposite a space in S1? Depending on which it is, it's a horizontal or a vertical move. Okay, so every alignment gives you a path. And again, you should see that two different alignments give you different paths. Okay? Because if they're different alignments, as you read them left to right, someplace they differ. And that means there's up to that point, the path that's being scoped out is the same, but at that point where the alignments are different, the path has to differ as well. Because these rules tell you something specific to do for each case. All right, so I'm going to augment this. Each path from 0, 0 to nm defines an alignment, a different alignment, and each alignment, different or unique, each alignment defines a unique path, or distinct path, or different path from 0, 0 to nm. So when we're talking about all possible alignments, we're really talking about all possible paths in this alignment graph. And by moving over to this pictorial representation, it's going to simplify a lot. This pictorial representation is going to simplify a lot of our thinking about what's a good alignment and how we find it. It's going to be a lot easier to describe an efficient algorithm by looking at this than just doing it symbolically, although we will do it symbolically as well. All right, now in this picture, now stop me if anybody has any questions about this, because this correspondence is really the key. It unlocks a lot of intuition, unlocks a lot of the details of what we're going to come to next. Okay? So does everybody believe that when you go home and close your eyes and meditate on this, you'll see the correspondence between paths in here and alignments? It may not be crystal clear at this moment, but it has to be clear enough that you think you'll get it when you spend the time. If anybody's utterly lost, let me know. Okay. Now, in this little graph, in this picture, this is called a graph in the computer science world, there's 3 numbers that are written here. Okay? They're all number 1. And what they are, these are the edges that go into a node where the corresponding characters are identical. Okay? So this edge coming into here, this arrow coming into here, has an N associated with that column and an N associated with that row. And remember what the rules of the alignment are. If you go along a path that takes this edge, this arrow, you're going to end up putting N opposite N. So that's a match. And similarly, if you look over here, this is N opposite an N, that's a match. And this is A opposite an A, that's a match. And actually, those are the only 3 possible matches that exist. Every other diagonal in here specifies a mismatch. It ends up putting 2 characters opposite each other that are not the same, so it's a mismatch. Okay? And we already said that every vertical and horizontal, let me do that again, every vertical and horizontal edge ends up putting a space in. So we know spaces cost -1 in our original objective function that I started off the hour with, but it's now gone. So what I'm getting to is this. If you have a path that specifies the alignment, and if you count a -1 for each edge that I did not put a number on, that was just for cleanliness, just to keep this from being cluttered. But if you put a -1 on every edge that doesn't already have a number on it, and you have a 1 on these 3, if you take a particular path from 0, 0 down to NN, and you add up the numbers that are on there, some will be 1s possibly, some will be -1s. But that sum is equal to the value of that alignment. Okay? So alignment graph for strings Dan and Ann, the weight on each edge is -1, except for the 3 edges marked in the figure which have weight +1. So just imagine that there's a -1 written on each of these edges where I don't have the +1. And then the claim is related to this one. Claim for any path from 0, 0 to NM, the sum of the weights on the edges. Edge, by the way, is just a mathematician's way of saying arrow. Okay? The graph world name for these things. The weights on the edges in the path, that sum is exactly the value of the alignment. Okay? So let's try a few examples like this one, a rather bad one. So this is a -1, -1, -1, -1, -1, -1. The sum along here is -6. And that's exactly the value of this alignment. Remember, you get a -1 for each space. You get a -1 for each mismatch, and a +1 for each match. So you get a -6. Now, now that we know that, what are we trying to do? And whose phone is that, anyway? I don't think it's anybody in the class. So what are we trying to do? We're trying to get an alignment whose value is maximum over all possible alignments. Alignment whose value is the biggest over all possible alignments. So in terms of this picture, in terms of this graph, and knowing now what we know about the relationship of paths to alignments, what are we trying to do? What kind of path do we want to find from here to here? One that has a total sum that's very small, that has small negative sum? Or what? The what? Yeah, what we're trying to do is find a path from here to here whose sum, total sum or total distance is often called, whose total distance is as large as possible. Because each time there's a positive number, that's a match. Each time there's a space, it's a negative number. Each time there's a mismatch, it's a negative number. So we want a path which has a large positive value, or a large value. I mean, positive would be great. It doesn't have to necessarily be positive. So just eyeballing this, just looking at this, what looks like a good path? You'd like to pick up these two diagonals that have a 1 on them. It's clear you can't get all 3 ones. There's just no way to have a path that goes through all 3 of these. But you can get 2. And what that path looks like is this. Okay? And so you get a positive 1, minus 1. It has a total of 0. And what alignment is that? Okay, using our rules, going vertically, you're using up D from Dan, but nothing from Ann. So that's a D against the space. Then you have 2 diagonals. So now you're placing characters opposite each other from the 2 strings. And finally, you have a horizontal here. And a horizontal, again, means that you're using up something from S2 and nothing additional from S1. So that's the alignment that has value 0. And does it look like there's any path that gives you a bigger sum than this one? I mean, just intuitively, it doesn't look like there's a path. Well, actually, we could make that formal because we've already said there's no path that uses all 3 of these. Okay? And every path, now I better take it back. I was about to say every path has the same number of edges, but that's wrong. Okay? Because this diagonal only has 3. But at any rate, this looks like the path that's going to have the largest possible value, which is 0. Yeah?
There's another path for equal.
There's what?
Another path that is 0.
There could be another path that's 0. Have you found one? What is it? Which one? Down diagonal, right diagonal. Yes, okay, so there's another one. And let's look at what that is. Down diagonal, right diagonal. Okay, so this is a -1 and this is a 1. And this is a total 0. And that one still has the same D and the A with A. And then all this is really doing is putting that space there and that one there. These are two, the previous alignment and this alignment are co-optimal for this objective function. If you were to put this into X per L, Ann and Dan, with exactly this model of no weight matrix, okay, 1 for a match, -1 for a mismatch, -1 for a space, you should see that you would get in the right polygon these two co-optimals. Okay? So this relates to last lecture where we were talking about co-optimals. So these are equally good under this particular objective function. All right, so now we know what we want. In order to find the best alignment, so in order to find the alignment that maximizes number of matches minus number of mismatches minus number of spaces, try to find the path from 0, 0 to NM with largest edge sum, also sometimes called distance. It's hard to think of a negative distance. I mean, if these edges actually, but anyway, that's the terminology. People talk about those things as distances. All right, now is this clear, this transformation? We've transformed what an alignment is to this picture. We've now transformed the alignment question to a question in this picture. Did we make any real progress? We didn't have a method previously for finding the best alignment. Now we have a problem that's got different terminology, but are we any closer to a solution? Yeah. You're asking why there's a 0, 0 in this graph? Well, the 0, 0 is so that we can have spaces put in one sequence before we're using any character of the other sequence. If I just had the graph without the 0 row, without the 0 column and 0 row, it would be starting here. And it would basically be saying I have to put D against A, or it would be hard to know what the interpretation is. So far, I've interpreted where you arrive to as what you do with the character for that row and column. What would you do with the D and the A if we started there? But having a 0 row says I can move along that row consuming characters from S2 without ever using anything from S1. So I'm putting spaces opposite those. Or similarly, going down the columns, I can do the same thing. Sorry, what?
They're trying to create something for our methods by inserting two spaces at the beginning. This is what we do, right? We're inserting two spaces in the sequence right at the beginning before we make anything else.
I didn't catch that, but I think you're right. Yeah, sorry, I didn't really hear it clearly. I'll remind you to try to speak in your microphone, which will help me and the listening audience at home.
I'll ask about it later.
Okay, good. All right, so now we have this problem. I want to find the path that goes from 0, 0 to NN with the biggest total sum. And I could, again, just enumerate all possible paths, but we already know, well, how many possible paths are there, by the way? Does anybody either know a formula or know where I can find a formula for that? Yeah.
You can sum up all the ways you can reach certain points and add it up.
We could. What you're saying is we could think about it. We could do that, but
Add it up.
For example, for the 0A,
yeah.
there's one path to that point. And if you diagonal, then you calculate how many paths you can get to that point.
Yeah.
And just keep adding up.
Yeah, that's true. We could get a recursive kind of approach to counting how many paths there are to each point. But there's a simpler way. I want to know how many paths are there from 0, 0 to nm. And I don't want to do a lot of work right now. I just want to turn a page, perhaps, and find it. Yeah? It's what?
NM?
N times m?
Yeah.
No, n times m, no. Too small. What?
The exponential n plus m over exponential n.
Not right. Factorial, yeah, maybe, yeah. It's what? 2 to the n plus m? 3 to the n plus m? No. 2 to the n plus m? No. Okay, here's the point. We today argued that every path gives you a different alignment, and every alignment gives you a different path. So the number of paths is exactly equal to the number of alignments. Okay? There's a one-to-one correspondence between each path from 0, 0 to nm and a different alignment of S1 and S2. Okay? That's the whole point of today's lecture, essentially. And we've already come up with a formula for the number of alignments. I don't mean you have to know it off the top of your head, but we already have it, and it involves a summation of product of factorial, of binomial coefficients, and so on. So the number of paths is exactly equal to that same formula we already had. Okay, that's the answer I was looking for. Okay. So we can't, again, for the same reason, we're not going to try to enumerate all those paths. But actually, somebody suggested how we could calculate the number of paths sort of on this picture here. And that turns out to be a very useful observation, which leads us really to how we're going to calculate the path that has the biggest sum. We're going to say, what's the best sum of a path that goes from here to here? Of all the possible paths that go from this one to itself, what's the biggest possible value you can get? 0, because really the only path is just to sit there. Because of the way the edges go, the arrows go, you can't do anything else. Then we might ask, what's the best possible, by best I mean what's the biggest sum we can get in going from here to here? -1. Actually, there's only one way of doing it. Okay. What's the biggest number I can get by going from here to here? -1 again, because there's only one way of doing it. All right. Now, what's the biggest number you can get by going from here to here? That's -2. Again, there's only one path that even gets you that way because of the way the arrows go. That's all you can do. And similarly, to get to here is -3. And to get to here is -2. And to get to here is -3. Okay? So the method I'm trying to introduce now is going to finally figure out what's the best way of going from here to here by figuring out what's the best way of going from here to each of the other possible points in this graph. And the way we start is with the really easy ones. The easy ones are the ones I just did, along the first row and along the first column, or the 0th row and 0th column. Okay, now I can ask about this one. What is the, of all the paths that can take you from here to here, what's the path with the largest sum? It has a -1. Just go directly, because if you went this way and this way, it would be -2. Or if you went this way and this way, it would be -2. So this one has a -1. Now, you can see that directly by saying, okay, the path was either this one or this one, or the path was this one and this one, or the path was that. But the way I really want you to think about it is the following. To get here, because of the way this graph is laid out, you either have to come from here, your nearest node, your last node you're in before you get to here, either has to be this one, or it has to be this one, or it has to be this one. If your last, in either case, well, if the last node that you visit before you get here is this one, then the total distance to here that way is the total distance to here plus what's on here, which is a minus 1. If you come through this node as your last node, then the distance along that path is whatever the distance was to here, which is minus 1, plus whatever the distance is along this edge, which is minus 1, that's minus 2. Similar reasoning tells you this is minus 2. Okay, let's make this a little more interesting, perhaps. Let's say I want to go from here to here. What's the best way? That is the path with the largest sum on it. I don't want to think about all the possible paths that get you there. Already we're seeing that's growing to be a large number. I want to apply that logic I just went through. The logic said, if I'm going to get here, the last node I visit before I get there either has to be that one, or that one. Because that's the way the graph is laid out. If it's this one, then the total distance of that path would be whatever the distance was to here, which I know was minus 2, plus this distance along this edge, which is minus 1. So that would be a total of minus 3. If it's this one, it's the distance to here, which is minus 1, plus this edge distance, which is another minus 1. That gives minus 2. If it's through here, it's the distance to here, which is minus 1, plus that one, which is minus 1. So I have 3 different numbers to think about. Minus 1. Sorry, this way was minus 2. This way is minus 2. And this way is minus 3. What's the biggest of those?
Minus 2.
Minus 2. So this one gets a minus 2. And the main thing to point out is that when I was figuring that out, I didn't think about all the different possible paths from here to here. I just thought about 3 cases. Either the best path came through here, or it came through here, or it came through here. Now, if you think about this and continue it, you'll see the idea of an efficient algorithm. But we will pick this up next time and do it in complete detail.